workshops. I think maybe everyone is expecting to have an in-person meeting very soon next year. Now we have too many virtual meetings over the last 3 years. I think they will be the last one virtual meeting. Now we plan to have an in-person meeting next year. Right. Okay, I will.
All right, everyone,
Okay.
Let's get started. Welcome
Okay.
to the international webinar series on advancing remote sensing application for the sustainable development of the oceans, marine and coastal resources. Pretty long name. First off, let me briefly introduce myself. I'm Tashanat. I'm an academic faculty at Burapha University School of Marine Technology. I will serve as a host today. And we have totally 14 speakers spreading across 5 weeks. And we try to switch moderator each week. And for the first week, we're gonna start with three speakers today, and I will also serve as a moderator for this first week. And first of all, I would like to invite Wenxi.
Okay.
The
IOC-WESTPAC office, right? Yeah, thank you very much, Touchnet. I think you know, I really want to express our sincere appreciation to you and also our colleagues in the Burapha University, particularly the Faculty of Marine Technology. You know, all colleagues there for your hard work and also tremendous effort that has been made in making this event possible. I also want to thank other, partners like the Department of Marine Coastal Resources of Thailand and the Asia Oceania Group on Earth Observations, AOGO, right? For their passion and also enthusiasm for promoting the remote sensing technology and the application for the sustainable development of ocean, coastal, and marine resources. So particularly, I would say, you Touchnet, I think over the last several months, without your, their excellent coordination and also hard work, I think that events couldn't be possible today. So I think it's owing to the common interest and the vision we shared for advancing the remote sensing, particularly its application for ocean sustainability, that make the events happen today. So needless to explain how importantly all of us, I mean, sitting here, we should advance remote sensing development in such a kind of a, very vast developing region, and also with a very high reliance on ocean for many, many purposes, job and livelihood. So I wish to thank also our all eminent speakers for taking your time. Today we have 3 speakers, right? And totally we have 14 speakers for taking your time, sharing your latest knowledge, good practice and experience, as well as lessons in developing remote sensing application in your different fields. I do expect your engagement won't just stop with the presentation today, but keep engaged in our future remote sensing activities in the region. So I think, I believe, the expectation from all organizers finally would go to all participants. So while you enjoy the presentations, please do consider how we can enhance the international cooperation jointly on remote sensing and its application for the sustainable development in the region. So with this, I wish the meeting a great success and look forward to more concrete cooperative opportunity in a very near future. Please be sure that we will continuously organize the remote sensing workshop in a very near soon, I think in an in-person mode. So I will also to conclude my very short remarks by inviting our dearest colleagues, partners, Professor Sarah Wood, the Dean of Faculty of Marine Technology at Burapha University, to give some remarks. Right, I give the floor back to you. Right.
Yes. Thank you, Mr. Wensi and IOC-WESTPAC Secretary, distinguished guests, our speaker and moderator, and our audience from many countries from our Asia Pacific region. This is a great pleasure for me and our faculty and also Burapha University to have all of you here to attend the webinar series. Of course, we would like to see in person in the near future, as Mr. Wensi said, and I do hope this webinar series can be acted as a collaborating platform for all of you in the future, not just only attend the seminar, and we hope we can have some project or we can share an idea, we can share methodology, we can get idea to work together in the future. With regard with the sustainability of the ocean and marine and coastal resources, Burapha University and Faculty of Marine Technology also commit a broad range of activities under the guideline of SDG and UN Ocean Decade Action. We have worked toward a numerous projects, and our faculties and staff also contributes to a lot of projects in Thailand, and we hope to extend into the regional scale. And yeah, it is practically essential to say that remote sensing become a necessary tools as a part of the ocean observing, monitoring, and forecasting system. We have employed many applications of remote sensing in taking care of our marine and coastal resources. And I myself am working in a marine spatial planning, and I can see the essential of remote sensing very much. This means a lot. And on behalf of Burapha University, we co-hosted international webinar series on ocean remote sensing applications with initiative and support from the IOC-WESTPAC and Department of Marine and Coastal Resources. We would like to express sincere gratitude and profound appreciation to Mr. Wensi and Dr. Somkiat Khorkiatwong from the WESTPAC office for their support and encourage and close coordination throughout this project initiative. And I also hope the webinar series, this could be enjoyable and intellectual stimulating. It will be a good start for sharing experience, exchanging lessons learned, and stimulating the upcoming idea. We are looking forward to seeing fruitful outcome and give a further enhanced regional capacity building and bring us many other opportunities to work toward achieving the 2030 agenda. And thank you everyone again to come and see. And I hope we can see all of you along the webinar series. Thank you very much.
Thank you, Wensi and Dr. Sarawut. We're gonna move on to our presentation from three speakers today. So let me introduce the first speaker today, Dr. Derek Manzello. He's coordination of the NOAA Coral Reef Watch. He worked at the Center of Satellite Application and Research, Satellite Oceanography and Climatology Division at Maryland. So he's gonna talk about like Coral Reef Watch and its decision support to in the warming climate. Please, Dr. Derek.
Thank you so much. Can everyone see my screen okay?
I see my face. Oh,
okay.
Oh,
All right.
Perfect now.
Okay, good.
All right, thank you so much. Thank you so much for the opportunity to present today. I very much appreciate it. My name is Derek Manzello, and I'm the coordinator of NOAA's Coral Reef Watch. Today, I'm going to give you a brief overview of Coral Reef Watch's main data products. Coral Reef Watch became an official program in 2001, but the work actually began in about 1997. NOAA was able to predict that the Great Barrier Reef would bleach in 1998, well before the Australians were aware of it. So Coral Reef Watch has been providing decision support tools to researchers, managers, and the public for the past 3 decades. Coral reefs are biodiversity hotspots, often called the rainforests of the sea. Now, approximately 25% of all marine species associate with coral reefs at some point in their lives. An estimated 1 billion people benefit directly or indirectly from the ecosystem services provided by coral reefs. The total economic value of coral reef services in the United States alone, including fisheries, tourism, and coastal protection, is estimated at over $3.4 billion per year.
Derek, sorry to interrupt. Can you hide the bottom button?
There we go.
Thank you.
Sorry. Reef building corals live very near their upper thermal limits. If ocean temperatures are higher than average by as little as 1 to 2 degrees Celsius during the warmest part of the year, or for a month or more, corals will experience bleaching. Coral bleaching is the breakdown in the symbiotic relationship between the coral animal host and its algal symbionts. The algal endosymbionts provide up to 95% of the coral's food, but the symbiotic relationship is highly sensitive to heat stress. The algal symbionts are expelled by the coral animal because high temperatures coupled with high solar radiation cause the algae to become toxic and produce free oxygen radicals that damage the coral tissues. When a coral loses its algal symbionts, it turns white or bleached because the symbionts provide much of the coral's color. When a coral is bleached, it is still alive, but in a state of slow starvation. If the heat stress persists, the coral will die, but if temperatures cool off, the corals can recover. Now, the damage that corals experience from marine heat waves is a function of the duration, or how long the heat stress occurs, plus the magnitude of the heat stress anomaly. Corals can recover from bleaching if the heat stress subsides, but they will have impaired growth, reproduction, and be susceptible to disease for 2 to 3 years after they recover from the bleaching. To illustrate how detrimental coral bleaching can be, I'm going to briefly discuss the recent history of the Galapagos Islands. Now, here's a photo of a Galapagos coral reef from 1976. Now, reefs weren't discovered in the Galapagos Islands until the mid-1970s by Gerald Wellington and Peter Glynn. Up until that point, it was believed that coral reefs were generally absent from the Eastern Tropical Pacific. However, the discovery in the 1970s was somewhat ironic because just as the coral reefs in the Galapagos Islands were discovered, they disappeared. The first documented mass coral bleaching event that impacted an entire region occurred 40 years ago in the Eastern Tropical Pacific during the 1982-83 El Nino warming event. The Galapagos Islands were hit hardest of all regions. Approximately 95 to 97% of the corals in the Galapagos archipelago died. Not only did the corals die, but the entire ecosystem was lost as the coral reef framework was completely bioeroded down to the basement basalt. This photo from 2012 shows you that recovery has not taken place after the coral bleaching event. So when a coral reef experiences bleaching and coral mortality, this has downstream impacts to the high biodiversity that is found on reefs. Given the high sensitivity of corals to temperature, we at Coral Reef Watch and NOAA are primarily concerned with sea surface temperatures and particularly with thermal anomalies. We generate our own sea surface temperature product at Coral Reef Watch termed Coral Temp. Now, these images show sea surface temperatures from February 7th of 2022. I use these old plots for illustrative purposes because this coincided with heat stress and bleaching on the Great Barrier Reef earlier this year. So from these sea surface temperatures, we can infer heat stress by examining temperature anomalies in near real time. The anomalies that are relevant to bleaching are called hotspots. Hotspots are a measure of daily heat stress above the maximum monthly mean sea surface temperature for each coral reef pixel on the planet. The hotspots represent an instantaneous measure of daily heat stress. Any daily anomalies greater than or equal to 1 degree Celsius get summed over the past 12 weeks. This yields degree heating weeks. Degree heating weeks, or DHWs, are a time and dose measure of heat stress to the corals. From these products, senior scientist at Coral Reef Watch, Gong Liu, developed a very simplified version for how to estimate recent stress to coral reefs. This is called the Bleaching Alert Area product. And this shows you visually where on the planet there has been a bleaching warning or alert level during the past 7 days. All the reds in this plot indicate that the corals in those pixels were exposed to bleaching level heat stress during the past week. Now remember that these images are from February of this year and these are not current. The reason I didn't use current images is because if you look at the current image from November 14th, 2022, you can see that we're in between the Northern Hemisphere summer and the Southern Hemisphere summer. So things are starting to cool off in the Northern Hemisphere, as well as warm up in the Southern Hemisphere. So the plot looks a little bare right now because we're in between Northern and Southern Hemisphere bleaching seasons. So I wanted to briefly review hotspots and degree heating weeks so that it is clear. Our various categories are as follows. A bleaching watch occurs when sea surface temperatures exceed the long-term climatological maximum. This is when hotspots begin to occur. A bleaching warning occurs when the hotspots or anomalies are equal to or greater than 1 degree Celsius. Degree heating weeks accumulate as the summation of all the daily hotspots over the past 12 weeks. As I mentioned earlier, sea surface temperature anomalies of 1 degree Celsius for 1 month are associated with bleaching, and this would equal 4 degree heating weeks. When 4 degree heating weeks are accumulated, this is termed an alert level 1 because this is when bleaching is expected to occur. So a 1 degree Celsius thermal anomaly for 1 week equals 1 degree heating week. A 1 degree Celsius thermal anomaly for 4 weeks equals 4 degree heating weeks, and this is when we expect bleaching to start. If the 1 degree Celsius anomaly persists for 2 months, this would equal 8 degree heating weeks. 8 degree heating weeks equals an alert level 2 because this is when we expect mortality to start occurring on the coral reefs. So not only do we monitor heat stress in near real time, but we also produce a 4-month coral bleaching outlook product. This gives managers information about potential future heat stress for their reefs, answering the question, will my reef be at risk for bleaching soon? This forecast is model-based and utilizes NOAA's climate forecast system to provide weekly updates about possible future heat stress. This image shows the forecast as of November 15th. And I want to point out that there is bleaching level heat stress forecasted to occur on the Great Barrier Reef over the next few months, with the latest update suggesting bleaching may start around Christmas of this year. I now want to introduce you to our regional virtual stations. If you go to the Coral Reef Watch website and click on virtual stations, a Google Earth interface will open showing you the 214 virtual stations that are currently operational. Now for illustrative purposes, I'm going to focus on the Great Barrier Reef because it experienced bleaching just this past year. You can see the icon showing the location of the various regional virtual stations. If I click on the far northern Great Barrier Reef virtual station, this icon will pop up that summarizes the current sea surface temperature, hotspots, and degree heating weeks for the far northern portion of the Great Barrier Reef. Here you can click on the alert gauges or the time series data graph and data to get data products for this particular regional virtual station. So if you click on the alert gauges icon, a window like this will open. Now this panel on the left shows you current conditions at the virtual site as well as the outlook or forecast product for the next 12 weeks. These are broken down into the current condition in the top left-hand panel, weeks 1 through 4, weeks 5 through 8, and weeks 9 through 12. As you can see, the outlook product is predicting heat stress is going to intensify on the Great Barrier Reef this year. So the 4 gauges correspond to the heat maps and show you that an alert level 1 or bleaching is predicted to occur in the next 5 to 8 weeks. And then alert level 2 is predicted in 9 to 12 weeks. In the top right of this slide is a 2-year time series graph of sea surface temperatures at this location that shows you the accumulation of degree heating weeks. Note that this area has experienced bleaching 4 times in the past 7 years. Bleaching occurred on the far northern Great Barrier Reef in 2016, 2017, 2020, and 2022. And as you can see from this plot, the degree heating weeks scale is over here on the right, that this section of the Great Barrier Reef experienced about 12 degree heating weeks. Now you remember that the algorithm predicts coral bleaching and mortality will start occurring at 8 degree heating weeks. Now the bottom right shows you all years of data from 1985 to present for the far northern Great Barrier Reef. This black line here is this year's data starting in 2022. Now their degree heating weeks haven't yet started to accumulate for the Great Barrier Reef, but you'll notice that this black line is among the hottest on record for the far northern Great Barrier Reef. Now, Coral Reef Watch also serves other satellite and model-based decision support products. Now, these include a marine heat wave watch product, a coral disease risk product for Hawaii, a light stress damage product because the bleaching response is due to the interaction of high temperatures with high light. We have an ocean color monitoring product for Puerto Rico and Hawaii, a suite of thermal history metrics because we know the history of thermal stress and the ecological memory of a reef can influence future bleaching. Finally, we also produce a larval connectivity model for Florida and Hawaii. So from 2014 to 2017, there was a third global coral bleaching event that took place. This was the largest and longest bleaching event on record, with many locations experiencing multiple bleaching events over this time frame. The graph on top shows you the max heat stress or bleaching alert area product during the event, and the one on the bottom is the animation of the heat stress rolling through the global ocean over the 3 years. More than 75% of the world's coral reefs experienced alert level 1 or 2, and more than half the reefs experienced multiple bleaching events over this 3-year period. Now, the third global coral bleaching event is currently being summarized in a manuscript that is currently under revision. I wanted to briefly step away from the pure science and show you all visually what the 2014 to 2017 global coral bleaching event actually looked like. This photo shows you a coral reef in the Florida Keys undergoing a severe bleaching event. One of the first places that began bleaching during the third global coral bleaching event was Florida in the United States. 2014 and 2015 were the 2 warmest years on record for the Florida Keys, and the corals experienced back-to-back bleaching during these years. In April 2015, the Chagos Archipelago in the Indian Ocean, which is one of the most remote reef regions on the planet, experienced bleaching. Here is a picture of some table acroporid corals that just started to bleach. Unfortunately, most of the corals in this picture were confirmed to have died from the event. Now, corals are not the only thing that bleaches. Clownfish anemones harbor algal symbionts just like corals. Many of you probably know that clownfish use these anemones to escape predators. So if the anemone bleaches and dies, it's likely that the clownfish will be more exposed to predation. For comparison, this is what a healthy anemone is supposed to look like. So heat stress on coral reefs has direct and downstream impacts to the high biodiversity that inhabits coral reefs. I now want to give a very recent example of bleaching on the Great Barrier Reef just this past year that illustrates the utility of Coral Reef Watch's products. Approximately 1 year ago, our Outlook product began predicting high levels of heat stress for the Great Barrier Reef. So this is from the Outlook product from December 7th of 2021. And you'll see that the most of the far northern portion of the Great Barrier Reef was predicted to experience an alert level 2 bleaching condition over the next few months. So these predictions were much earlier than the typical bleaching season for the Great Barrier Reef. So we did a deeper dive into the data. What we found is that minimum temperatures from November to December on the Great Barrier Reef were higher than all previous maximum temperatures over the same time period for 87% of the pixels. Thus, the majority of the Great Barrier Reef started the Southern Hemisphere summer with more accumulated heat stress than ever before. We sounded the alarm and published a paper saying that bleaching was likely on its way. This figure clearly illustrates that sea surface temperatures on the Great Barrier Reef were much higher than ever before in the satellite record during the second half of 2021. Again, this is sea surface temperature data from one of our virtual sites on the Great Barrier Reef. So the 2021 data is the dark black line. And you'll notice that during the second part of the year, this black line is higher than all the other lines in the record. So 2021 was the warmest year on record from November to December. Now this animated figure shows you the progression of heat stress as it developed along the Great Barrier Reef at the end of 2021 and the beginning of 2022. A few things to notice. First, the heat stress was focused on the far northern portion of the Great Barrier Reef. And second, there was an initial heat stress event followed by a brief respite due to Tropical Cyclone Seth, which caused sea surface temperatures to cool temporarily. And then a second heat stress event took place after Tropical Cyclone Seth. So in essence, there were two heat stress events that occurred on the Great Barrier Reef during the most recent Southern Hemisphere summer. So the Great Barrier Reef Marine Park Authority and the Australian Institute of Marine Science conduct bleaching assessments on the Great Barrier Reef. So following the aerial bleaching surveys undertaken by the Great Barrier Reef Marine Park Authority and the Australian Institute of Marine Science, Dr. Neil Canton confirmed that the bleaching prevalence and severity of the event corresponded with the predictions from Coral Reef Watch's products. In summary, the Great Barrier Reef was hit with its sixth mass bleaching event since 1998. Perhaps most concerning is that this was the fourth such bleaching event in the past 7 years for the far northern portion of the Great Barrier Reef. So we are starting to get close to annual bleaching taking place. Now, most climate models predict that annual bleaching for most of the world's coral reefs will begin sometime between the years 2040 to 2050. So it's concerning that annual bleaching is getting close to happening on the Great Barrier Reef right now. This suggests bleaching impacts are occurring sooner than what is expected based on the climate models. So Coral Reef Watch products predicted the event in advance and predicted the severity of the event as it unfolded. Last, this was the first bleaching event on the Great Barrier Reef that took place during a La Nina. Now, historically, cooler sea surface temperatures coincide with La Nina conditions on the Great Barrier Reef. But during this most recent La Nina, sea surface temperatures were much more elevated. Now, unfortunately, conditions on the Great Barrier Reef right now look quite similar to what they looked like last year at this time, as our Outlook product is once again predicting bleaching on the Great Barrier Reef to begin in late 2022 and early 2023. Now, we are monitoring this closely and hoping that some regional cooling takes place between now and the Southern Hemisphere summer. In conclusion, Coral Reef Watch has been doing this since 1997 and has been an incredibly valuable resource for documenting and understanding the impacts of climate change on coral reefs. We are still the only global coral bleaching warning network. We engage with resource managers, scientists, and the public to help develop, improve, and implement these products. And our products are currently being served through multiple collaborators, online data portals, such as the Allen Coral Atlas. I'd like to thank the Coral Reef Watch team, particularly Gong Lu, Jackie Delacour, Eric Geiger, William Skirving, Blake Spady, and Ben Marsh all contribute significantly to making Coral Reef Watch an excellent program that it is today. Thank you very much for your time.
Well, thank you, Derek, for comprehensive talk. We have time for questions. Wensi, please.
Yeah, thank you very much. Thank you very much, Derek, for joining us in the evening time. I think evening time, right? I think this is a very wonderful operation work that has been done by NOAA, by combining the remote sensing and the in-situ observation and the modeling group together, right? And also, I think a local stakeholder together. So my question also related to operational aspect. What kind of idea that make those people work together, remote sensing group, coral reef group, modeler group, work together to come up with this kind of very comprehensive. My second question about resolution. So 5 kilometers. There any plan for NOAA to develop, higher resolution, 2 or 3 kilometers, or even better, right?
Yeah, I mean, currently we have a proposal in with the University of Reading to develop sea surface temperature products that could be at kilometer resolution. So we're hoping to be able to develop those in the next several years.
Okay. So my first question, Derek, how there people from different disciplines work together? There are big program, operational program at NOAA supporting this kind of the joint efforts, or something else driving this program for a long time, right?
Yeah, NOAA, the National Oceanic and Atmospheric Administration, has a coral reef conservation program. So this was signed into law by President Bill Clinton back in 2000 that created the Coral Reef Conservation Program. So since 2000, Coral Reef Watch has been a program. And how it came together, it was actually, I think, through some of the work of the Clinton administration, and Al Gore at that time was vice president, because we knew coral bleaching was a serious, significant problem that was taking place. And it was starting to happen all over the world. So there was a lot of concern about this phenomenon. So the US government actually invested resources in developing Coral Reef Watch to better understand climate impacts to coral reefs around the world.
I see. I got it. Right. Yeah.
And Dr. Sarawut, please.
Yes, thank you. And thank you for Derek for your great presentation. I am your customer. I'm not a customer. I am the user of your NOAA Coral Reef Watch too, because I am working in the coral reef. And we've been using NOAA Coral Reef Watch for years. And we can see that they have a benefit to us too. As my first, I would like to, and Dr. Wenchi said, in Thailand, we have like a smaller coral reef.
Right.
And so we are looking for like a higher resolution of the program. This might be very good for us too. And I have a question. This year, if the heat, the sea surface temperature is moving up north, because as you present around the Southeast Asia, we are still fine. But I don't know if like late of December or January, somewhere around Thailand and somewhere around Southeast Asia, are we at risk of coral reef bleaching again this year?
I'll have to go back and check our Outlook product
Right.
to see. As of right now, I don't believe so. I believe Thailand generally bleaches during the northern hemisphere summer. So I think we're somewhat
May and June. Yeah.
Yeah. So I think our forecast only goes out 4 months, so we can't predict next June yet, but we can predict southern hemisphere bleaching. And again, it looks like there's going to be a big area of warm water in the Coral Sea, south of Papua New Guinea. But again, I would have to go back and review our Outlook product to see specifically if there's more regions in the Indo-Pacific region that are at risk.
Thank you.
Direct, I also have some technical question. Like previously, we know that warmer water will be enhanced during La Nina, but recently, like El Nino event also make the sea level drop down. Are you gonna consider sea level anomaly together with SST anomaly in the reef alert? As
of right now, no, but that's actually a very good idea for a future product, especially with changing sea level and changing El Nino events. So no, I really like that idea. NOAA does have people that work specifically on sea level height, so that might be a product that's worth looking into the future.
And 5 kilometer product is still based on AVHRR thermal infrared, right?
Yes, that's correct.
I was wondering, we should consider skin SST or bulk SST in terms of reef health.
Yeah, I mean, bulk SST and more ocean heat content type products are where we're looking to into the future to try to better estimate thermal stress on coral reefs, especially because we know there's a lot of variability with depth and temperature on the reefs.
All right, thank you. Next, Lalita, please.
You're mute, Manita mute. Okay.
Dr.
Hello.
Lalita.
Yes.
Yep.
Oh, mute again.
I'm sorry. Thank you very much for your talk. Do you hear me?
Yes.
Okay. I also would like to say thank you for your products, and I am as a every year. So for Thailand, we collect the coral bleaching situation for all over the Thai waters, and of course, as I follow your works very well, and we would like to improve our work as you recommend in your publication in many times that every places have their own unique unique condition, water condition, and also the local environment. For example, in many times that especially in the Gulf of Thailand, we report a lot of coral bleaching, but not only the temperature, but also the sea level lower during the mid of the year, during the summer. So, I mean, in Thailand, there are many physical factors that are making coral bleaching. So we also would like to improve, follow up your from the coral reef watch. We also would like to improve to forecast our coral bleaching in the to represent our real situation. something like that. So I mean, I just would like to share and say thank you for your work. It's really helped us to have the overview of coral bleaching status in Thailand and everywhere. Thank you.
Thank you so much. Yeah, I will say that we're always looking for more coral bleaching observations. So if you are a user of the products and you're observing bleaching and collecting data, you know, anytime you could share data like that, it helps us improve our algorithms to make the products better. But thank you very much for kind words. I appreciate it.
All right. Thank you, Derek. Let's move on to the next speaker. So next up would be Professor Teruhisa Komatsu. He was at Ocean Research Institute, the University of Tokyo. Of course, he published a bunch of papers, over 200 articles. He currently works at Japan Fishery Resources Conservation Association, formerly affiliated with Ocean Research Institute, Ocean University of Tokyo. His talk today will be about a case study of using remote sensing in aquaculture management. Please, Professor.
Thank you very much. Can you hear me?
Yep, perfect.
Yeah, okay, I start. Thank you very much. Kindly give me the chance to present my works. So I thanks to WESTPAC and Burapa University and DMCR. I start my talk. So I applied the remote sensing to the integrated coastal area management in Japan, especially in the aquaculture. Satellite remote sensing for integrated coastal area management is satellite remote sensing is a practical tool for monitoring coastal habitats and human activities such as aquaculture. How do we use this tool for realizing sustainable and healthy coastal waters with a high biodiversity and rich fisheries production? This is very important. To monitor temporal and spatial changes in coastal habitats and human activities, and to combine mapped data with an ecological simulation model. Today, I introduced this some example. We conducted work in Shizugawa Bay, Japan. So where is Shizugawa Bay? Shizugawa Bay is east coast of Tohoku region, Honshu Island, Japan. And you can see this area is a rheostat based chain here. Okay, so Shizugawa Bay is one of the rheostat bays on the sunny coast. Characteristics of a rheostat bay and the necessity of its management plan icon. So characteristics of a rheostat bay is have a deep sea bottom at the bay mouth. So they have a good water exchange, strongly influenced by the open ocean. On the other hand, the small rivers, only because rheostat bay is surrounded by the mountains near the sea. So small rivers flowing into the bay are surrounded by the mountains. In this setting, permit the active aquacultures because the wave is not so strong and protected. So, but on the other hand, the very suitable for aquaculture, the bay is overused with the aquaculture facilities. So we need a management plan to control overuse. So sandy coast aquaculture is developed and the most important fisheries in the coastal waters in semi-enclosed rheostat bays. Overuse of a bay is the biggest problem, like as many Asian countries. You can see this is a Yamada Bay, and the bay is most of a bay is covered with oyster cultures. This is the situation. But huge tsunami hit the Sanrik coast on 11 March 2011. This is a figure of the Sanrik coast, and the green is tsunami wave height, and light green one is modeled wave height. So this is Minami Sanriku is here. Shizuga Bay, about 14 height of the tsunami hit the bay. So huge tsunami hit mainly Sanrik coast and devastated aquaculture facilities like this. So why did we start to study Shizuga Bay after the huge tsunami? To develop a management method to realize sustainable aquaculture and sound marine environments in a Rias-type bay, funded by a Ministry of Environment of Japan. And this bay is 5 kilometers here and about 5 kilometers here. Okay. And I propose satellite remote sensing from monitoring to prediction for ICAM through ecological simulation model. Satellite remote sensing is practical for monitoring coastal waters to realize integrated coastal area management through visualizing coastal habitats and human activities. Archived satellite images permit us to understand what drivers or impacts have damaged present coastal environments. Advance of ecological simulation model can reproduce current environments and aquaculture and project those in the future under different scenarios of sea use. Visualization of future status obtained by the model is useful to discuss with stakeholders to set the management plan. One, mapping of coastal habitats with satellite remote sensing. We conducted the habitat mapping using a satellite remote sensing. And this is before the tsunami, 2009. And right-hand picture is just after the tsunami, 2012. You can see the orange color means seaweed beds. And green one is seagrass bed. And after the tsunami, green one is shrink, very small. So we can monitor and trace the change in the spatial distribution of seagrass and seaweed beds. And this is 2014, and we mapped 2014, and we provided to the Shizuga town to obtain the Ramsar site registration. So Shizuga Bay as a new Ramsar site, and this is Ramsar site is the site under the Ramsar Convention of Wetland, and this was accepted on the 18 October 2018. And our mapping results serve to registration of the site. And why this Shizuga Bay is registered as a Ramsar site? Because seaweed is boreal and also temperate seaweed mix distributed, and very precious migrant bird pass in winter here, and they eat the seagrass and seaweeds. And why mapping of aquaculture facilities needed? This is a human activities. So prefectural government appoint areas for setting aquaculture facilities, which are managed by branches of local fisheries cooperatives. So this is a Shizuga Bay, and permitted area is here. But this area is managed by each branches. In Shizuga Bay, 3 branches here. And but the branch office didn't know positions of aquaculture facilities. When we visited Shizuga branch in September 2011, the president, just after the tsunami, the president of the branch asked us make a map of the aquaculture facilities. So, and especially in the inland part of Shizuga Bay, oyster culture facilities are developed in the Tokura branch and the Shizuga branch. And this is a very important industry, fisheries. And also we can find 4 types of aquaculture facilities in Shizuga Bay. One is oyster and scallop and ascidian. And 100 meter and big buoy. And oyster culture uses like a raft, you know. And another is in winter, seaweed wakame is cultured using this small buoy and 70 meter. And from autumn to early spring, the coho salmon is cultured using the octagon with an edge length of 6.5 meter. This is feeding aquaculture. The other is no feeding aquaculture. So 3, detection of aquaculture facilities using commercially available high spatial resolution multiband image. So we use the GOI1 or others, and we produce the pan-sharpened image using near-infrared band with a spatial resolution of 2 meter and pan-chromatic band with that of 0.5 meter. So pan-sharpening means, for example, multibands and pan-chromatic. We using this pan-chromatic information, we produce the fine image like this. So this is an example of pan-chromatic sharpening. And right-hand side is we produce the pan-sharpened image over near-infrared band. And we can see that this is this one is octagon like this, and this red type is oyster, and this one is green is seaweed wakame. Okay, so you can we can distinguish using this, and this one is raft, oyster raft. So using this pan-sharpened image, we can distinguish easily the aquaculture facility types. To monitor aquaculture facilities in Shizuga Bay. So before the tsunami and just after the tsunami and 2013, 2014, 2015. So using satellite image and also aerial photography. So aquaculture facilities developed in the inner part of the bay. This is a Shizuga branch. This is a Tokura branch. And you can see the here more nearly the it's not a line, it's a band, you know. Very dense deployment of oyster cultures. And also, some area is, how do you say, the outside of the permitted areas. Some are like this. And the green one is seaweed wakame cultures. まあ、Shizuka branch is, we can distinguish each one. But in the Tokura branch, we cannot distinguish the one by one. But after the tsunami, you can see the very small in the 9 September 2011. And wakame is not cultured in summer. So, okay. So the oyster farmers, fishermen, recognize that the oysters are farmed and landed over a period of 2 to 3 years before the tsunami. But after the tsunami, oysters reached the shipping size in less than a year. Means the too crowded before the tsunami. But after the tsunami, the oyster grow very well. So fishermen oyster farmers decided to reduce the number of oyster culture facilities in the inner part of Shizugawa Bay through discussion using the map. And Shizugawa branch reduced the number of oyster facilities by 50% of 2009. And the Tokura branch reduced those by 70% of 2009. So you can see, before the tsunami, Tokura is very crowded. But after the tsunami, it's very small. This is 2009 is before the tsunami, and just after the tsunami, and 2015. Aquaculture facilities in the part of Shizugawa Bay is before the tsunami, and just after the tsunami, and present. And revolution to reduce oyster culture facilities by a third in Tokura branch and by half in Shizugawa branch. You can see this is a half. This is a third. Okay. So aquaculture facilities deployed in the inner part of the bay after the tsunami. Oysters reached the shipping size in less than a year. And now we can identify each line as the oyster line we can find. So V and rope types of seaweed, green, and oyster. And in Tokura branch, they control the number of seaweed wakame culture also. On the other hand, Shizugawa branch, the number of the seaweed culture is remain like as before the tsunami. And providing aqua facility data for acquisition of ASC certificate that proves sustainable aquaculture and respect for healthy marine environments. So we provided the map to this map, and Tokura branch obtained the ASC. ASC means Aquaculture Stewardship Council, and they admit the aquaculture, sustainable aquaculture, and respecting the healthy marine environments. And this is a certificate. Okay. So habitat mapping is very useful for like this acquisition. And revolution to reduce oyster culture facilities by a third in Tokura branch. This is a courtesy of presentation of Mr. Akihiro Dazai in Kobe on 20 October 2022. So 2010 and 2017, and increase or decrease from 2010 to 2017. So one production per one management entity of oyster culture is a kilogram. So before one entity produced the 1,790, but after the tsunami, 3,545 means 98% increase, so double. And amount of production per management entity of oyster culture, unit is 1,000 yen. Before is 3,308 80 yen かな。And after the tsunami, it's 1.5 so 50% increase. And the cost is before the tsunami like this, and after the tsunami. After the tsunami, it's about 50% decrease. And working hours per day is 10 hours per day. But after the tsunami, because number of the aquaculture facilities decreased, so only 6 hours. So 40% decrease. So it's a benefit, big benefit for the fishermen. And fishermen's awareness raising. And this is according to Mr. Kiyohiro Goto, president of the oyster farming in Tokura branch. Before the tsunami, the early bird gets the worm. Take before they take. Compete with each other. As long as it's good enough for me, as long as it's good enough for now. Break the rules. After the tsunami, enrichment of all members, think about those around us, share resources and prosperity. Think about the environment and the next generation. Think continuity and think 20, 50 and 100 years into the future. So they change their mind. 5. Ecological simulation model and satellite remote sensing. Left-hand side is a distribution of aquaculture facilities by remote sensing. And this data is used for the ecological simulation model. Can you see the number of numbers? So number means number of aquaculture facilities here. So simulation model needs initial conditions. So the simulation research use this mapped data as initial condition. And simulation output of oyster fresh weight in 2009 and 2014. And fresh weight of farmed oyster on 1st October, 1 year after culture. Okay. So left hand side is before the tsunami. And right hand side is 2014 after the tsunami, and they controlled the number of the aquaculture facilities by third. So this is a fresh weight of per individual of oyster. The 10 gram is here, okay? And before and after, you can see the differences. Before the tsunami is it takes about 3 years to shipping size, but after the tsunami, it takes only one year. And dissolved oxygen content near the bottom This is a very important index of environment. Before the tsunami, for example, this area is DO drops below 4 milligram per liter, means a very bad condition. But after the tsunami and reduce the number of aquaculture facilities, the bottom, the DO of near bottom is ameliorated. Can see. This means that it's a sustainable aquaculture. So prediction of marine environments in Shizuoka Bay by ecological simulation model with use of satellite remote sensing data and a computer. So prediction is the number and the arrangement of aquaculture facilities for realizing sustainable aquaculture in harmony with a healthy marine environment. So discussion on ecological simulation scenarios among Minami Sanriku Town, Shizuoka Bay Management Committee of Miyagi Fisheries Cooperative with us to explore the number of rafts and the deployment for sustainable aquaculture in harmony with healthy marine environment. This is a picture of a meeting. And we conducted the council for examination of future Shizuoka Bay with stakeholders. And we have a meeting here. Okay. So one example is the first council. This is a Japanese style meeting. You can see. And scenarios for prediction co-designed in 2017. Scenario 1 is in this area, we reduce the wakame culture to 75. And in this area is Acidia and scallops. But this is not so good. It's some death. So they some scenario of 75% of current level decrease. And scenario 2 is 50% and 50%, and scenario 3 is 25% and 25%. And the simulation model results of computation is current is here, and scenario 3 is, you can see, this is very good for wakame culture. Okay. Before is very low harvest, but after the this scenario 3, in very good, and also this one is also good. And wakame culture in the when we decreased by 75%, the production in this area is increased, and this is a potential production per wakame culture facility is increased. Like so, one in the Shizuoka branch, the current harvest could be maintained even if the number of rafts was reduced to 75% of the current level. The second possibility of not being able to keep current production if they are reduced by more than 50%, like this. Okay. So Shizuoka branch decided to reduce scallop and Acidian culture facilities and convert them to those of wakame seaweed culture according to the scenario 1. So summary 1, satellite remote sensing is a practical tool for ICAM through monitoring coastal habitats and human activities by visualizing their spatial distributions. Surveillance of coastal area needs information of temporal changes in coastal habitats and human activities, which satellite remote sensing can provide. Maps of habitats and human activities in coastal waters help stakeholders to discuss on conservation of habitats and revision of human activities. For ecological modeling simulation reproduces a realistic coastal ecosystem with the use of maps above mentioned and project a coastal ecosystem in the future according to scenarios co-designed by stakeholders. 5. The case of Shizugawa Bay shows that the satellite remote sensing and ecological modeling simulation realize sustainable coastal waters. Thank you for your attention.
Thank you for Professor Kumatsu for interesting talk. Of course, wakame is one of my favorite dish. We have time for a couple questions. Wensi?
Yeah, because I think other participants may be too shy or keeping a low profile. So I just take a first question like the strawman. So Kami-san, thank you very much. I think indeed we see a very clear example how the application, inform the decision, inform the policy. I think in this case, sustainable aquaculture, right? I think indeed for remote sensing, so it's pretty quite mature to map the aquaculture facilities, right?
Yeah.
Right. So that's why I think working together with the other field of science, ecologists particularly, and also agriculture expert, so we can see a very convincing results, sustainable management, right? But I noticed another issue in your presentation at the beginning. You said your work also include the coastal habitat mapping, seagrass and the seaweed. You can even distinguish, right, by different colors, green color and also gray color, right, in that bay, in the cover bay. How you can distinguish the two habitats, seagrass and seaweed? And what's the accuracy so far from your studies?
We published in 2012, and accuracy is 80%.
Yeah, right. Can distinguish very well seaweed and also seagrass.
Seagrass is and also we use some ground truth data, and we allocate the seagrass as we verify, and we not only mapping results. It's some we change if it is not true. We change the class. So we of course we rearrange the habitat, but this one is very very good. And how do you say the remote ecological simulation model uses this data as an initial condition for because simulation model use nitrogen based model, so which how do you say the animals and also the plants use nitrogen like this, and they calculate. Okay.
Right.
And are there any other questions? Perhaps I have one. I was wondering about the wakame aquaculture. It's not good for summer, right? Are you experiencing like longer and warmer summer, expanding?
No. In seaweed, we have a scanty growth season and luxuriant growth season in 1 year, and in summer they are very small. Okay, it's small, and they become growing since late autumn, and they become maximum in spring after they die. Okay, it's annual species, and they become very big in rapidly. And so in summer, no seaweed. For example, sargassum also in summer they disappear, and very small one, only like this. Northern hemisphere generally, most of seaweed become big in winter.
Mhm. Thank you. Next one, Dr. Wirod, please.
Very much for your good presentation. I just wondering when we research the project like this, then we move to operation for the policy people. How we have like a method to let them operate by themselves, because we cannot handle every
Yeah.
part for them. Thank you.
Yeah, this is a summer, edge cutting research for exploring the ICAM, integrated coastal area management. So we use we can use the ecological simulation model very fine scale. Yeah, I understand. On the other hand, the satellite remote sensing is not so complicated, and it's a very basic technique to produce the pan-sharpened image. So if you have no resources to calculate the ecological simulation model, but you can produce the aquaculture facilities map. This is very important. And you can discuss with the stakeholders. And for example, before the tsunami in Shizuoka Bay, the fisherman is always competed. So someone increase one aquaculture facility, the other also. And after that, it takes about 3 years. But after the tsunami, only 1 year they can the oyster reach to a shipping size. So the fishermen understand we need to reduce the number of the aquaculture facilities. If so, I think you can also persuade the fishermen or stakeholders using this kind of map and discuss with them. They know, maybe. But they cannot, how to say, accept the decrease. But if all members accept, they accept. Okay? That's very important. So I think, so for the discussion, the map is very important. Because visualization is very important.
Thank you.
All right, thank you, Professor Komatsu. We have
Yeah,
time
thank you
again
very much.
at the end for open discussion. So next speaker is Professor Tatsuyuki Sangawa. He is currently an associate professor at Tottori University of Environmental Studies. His area of expertise include modeling, remote sensing, and GIS. His talk today would be about operational coastal habitat mapping. Please, Professor Sangawa.
Okay, thank you, Jim. Thank you, introduction, Gemma. Could you hear my voice?
Yep.
Yes.
Okay. Okay. Good morning, everybody. My name is Tatsuyuki Sagawa from Tottori University of Environmental Study, and I also belong to WESTPAC Ocean Remote Sensing project as a steering committee member. Today, I'm talking about operational coastal habitat mapping using satellite imagery in Japan. This is the outline of today's my talk. Basically, I introduce Japanese mapping project about coastal habitat. As already Dr. Manzaro explained, coastal habitat such as coral reef really important for marine organisms, and seagrass beds and seaweed beds and mangroves and tidal floods are also important as marine organisms. As habitats for many marine organisms. However, these habitats are damaged all over the world due to many human impacts. Thus, it is important to monitor and conserve habitats for sustainable development for coastal area. In Japan, there are several monitoring projects for coastal habitats. And several agencies, several organizations conduct surveys. And especially a Ministry of Environment that could conduct surveys and target area is all Japanese area. And fishery agency, they also set a guide for coastal habitats, especially target is seaweed and seagrass. And under this guideline, each prefecture conducts surveys. And there is also a North Pacific Action Plan under UNEP, and include Japan, China, Korea, and Russia. Basically, Japanese NAPAP area is around here. And they also set a guideline and conduct mapping about seagrass and seaweed. And there are also universities or research institutes. They also conduct survey and develop the method for coastal habitat monitoring. Today, I'd like to mainly introduce activities conducted by Ministry of Environment. And I think activities of NAPAP, Dr. Genki Terauchi will explain next month. There are mainly two divisions in Ministry of Environment. First one is a Biodiversity Center of Japan. They conduct a natural environmental survey and also conduct a monitoring site 1000. Basically, the first one is a national mapping project, and the second one is a spot survey. This is a continuous spot survey. This is also important. And the other department is Office for Environmental Management of Enclosed Coastal Seas. Their target area is basically enclosed coastal seas, as included in their name. So I will introduce several projects today. First, about the mapping method, especially in Japan, until mid-2000, basically, mapping was conducted by traditional methods, such as interviews with researchers and specialists, or conduct a visual observation. In this case, visualization by diving, scuba diving, or observation from a boat using glass board. Or sometimes they refer to aerial photographs. Basically conducted visual interpretation by human, and draw a seaweed map or seagrass map like this, basically drawn by human. This is an example of previous map. From mid-2000, remote sensing, satellite remote sensing method also introduced in the mapping projects. And in Japan, several satellite images has been used. EROS is JAXA's satellite. And Spot, Rapid Eye, Iconos, Planscope, Worldview, Sentinel-2, Basically, these satellites are optical sensor, and spatial resolution is better than 10 meters. And simultaneously conduct field survey to obtain training data and validation data for remote sensing. For example, to obtain training data, we use acoustic video camera or echo sounder. And the map is created based on satellite images. So this is an example. So much more precise images we could create it compared with previous surveys. So from here, I introduce several mapping projects and results. This is an outline. First, I introduce a mapping project in Seto Inland Sea. Seto Inland Sea, located in west part of Japan, this area. Here, Tokyo, and here is Seto Inland Sea. In Seto Inland Sea, there are a lot of islands, and so there are many, there are a lot of seaweed and seagrass beds, and also there are tidal flood. And the mapping project was conducted from 2015 to 2018. In this project, the habitat map was created based on remote sensing technique. But the interviews were also conducted to compare with previous results. This map, for example, this green area is seagrass or seaweed map created in this project based on the satellite remote sensing. So this ratio is very precise. And this pink polygon is seaweed or seagrass map created in previous survey, basically based on interviews. So we cannot directly compare with these two results. So we also conduct interviews. These are outline of seagrass, seaweed, and tidal flood map. Here, total area of seagrass and seaweed area is almost 15,000 hectares, and tidal flood area is almost 11,000 hectares. In the image, actually, seagrass area or seaweed area is overlapped on the tidal flood too. So you don't see all the total flood, tidal flood area, but tidal flood area is also large as well. This map shows the changes of seagrass and seaweed area from previous survey. Basically, in the color, green area, basically seagrass or seaweed increase, and blue is maintained, and orange is decrease. So basically, each part, most of the places, seagrass or seaweeds increased. And west part, some places, in 4 places, seagrass or seaweed decreased, but in other places, almost same, not so changed so much. This and the next is about the tidal flood area changes. Basically, color expresses the same meaning. So when you see, basically tidal flood area not so changed so much, but to increase in some places. Actually, and here several artificial tidal floods have been built. Okay. This is the outline of the project for the Seto Inland Sea. I introduce other project. The project is tidal flood mapping in IOC. Here, located west side of Central Inland Sea. This area sea is also really large, and it will include large tidal flood area. And this is updated tidal flood map. Basically, this brown area is a tidal flood, and total area is 13,000 hectares. Here we also compared. Here basically they also compare the tidal flood map area with the previous survey, and basically a 6% increase for total. So basically not so changed so much in this area. Next, I introduce coral reef mapping in Seksei Shoko. This place located in Okinawa Prefecture, southwest part of Japan. Here we can find a lot of coral reef, and last time mapping project was conducted in 1991, and this time map was updated in 2017, and color concerning our color, basically color related with coverage. Basically green area coverage is 50 to 100%. And yellow is 5 to 50%, and red is 0 to 5%. And here we can compare this map, because even in 1991 map was based on aerial photograph. So when we compare this map, apparently a green area, I mean a high coverage area, decrease and change to red or yellow area. In this map, coverage area is divided in 3 areas. And apparently, in all 3 areas, coverage of coral reef have been decreased since 1991. So far, I introduced several mapping projects, but I also introduced monitoring site 1000. This project started since 2003 to monitor Japanese nature in long time. So this includes not only coastal habitat, but include forest, basically all the nature in Japan. And it is important to notice degradation of nature in early stage. So this monitoring site was set. And this site includes sites for coastal habitats. So I show several examples. For example, 6 sites 6 sites are set for seagrass beds, and also 6 sites were set for seaweed beds. And basically, in these sites, precise survey have been conducted every year. Basically, every year, surveys based on photos have been conducted. Basically, quantitative research by visual observation also conducted. And every 5 years, quantitative researches by sampling also conducted. Basically, same for the tidal floods and rocky coasts. 6 sites for tidal floods and 6 sites for rocky coasts were set. And concerning about coral reef, much more sites were set. Basically, 25 sites for coral reef. And in this case, for coral reef, every year, research for coral coverage is conducted, except remote locations. And every 5 years, also research for coral coverage is conducted, including remote location. Basically, these surveys are visual observation. Okay. This is a summary of seaweed beds and tidal flood in Japan. Basically, a distribution map was updated in most places in recent survey. Basically, from 2015 to 2021, map was almost updated, but in some places still in progress. So here I couldn't show total area. In this survey, basically a map is updated, but changes and reasons were not necessarily analyzed in each mapping project because, as I explained before, mapping method was changed compared with the previous survey. So basically, it's difficult to compare directly. Concerning about the coral reef distribution map were updated in most places as well. And this is a total number. This is a reported number, reported area for coral reef for each area. And total area is about 42,000 hectares in Japan. And Yakushima Islands are Tanegashima Islands. This belongs to this Osumi Islands and Tokara Islands. The distribution area of coral community hadn't seen changes. And concerning about Takarajima Islands, Yakushima Islands, distribution area of coral reef tends to increase significantly. And the relationship between coral reef and coral reef distribution and land usage also surveyed in Amami and Miyako Islands, but no relationship was confirmed. On the other hand, relationship between coral distribution and sea temperature is recognized in Amami and Miyako Islands. So far I quickly introduce Japanese habitat monitoring projects. And here is pick up several subjects of coral mapping in Japan. First, about remote sensing technique itself. Basically, cost of satellite data analysis is really expensive. Because mainly the high spatial resolution satellite images have been used, but these satellites are really expensive. And there are uncertainty of limitations, limitations related to depth, transparency, observation conditions. These limitations are not necessarily cleared. So should be cleared in the future. And concerning about field data, basically there are lot of type of data because data are collected in variable ways for variable purposes. And data provided in each project, but complex to access, sometimes not easy to access. And as I explained, data managed in each project, however, data not necessarily managed from integrated point of view. For example, area of singular seaweed beds in all Japanese coasts are not officially summarized now. And data are not easily accessed by international researchers because data sites are basically provided by Japanese and English sites are still poor. So I expect to be improved in the future. And future perspective, concerning about satellite image, this year, launching of JAXA's new satellite, SL3 is planned. This satellite has an optical sensor with a high spatial resolution. And I expect this satellite contribute to coastal habitat mapping, especially in Japanese area. And mapping project in Japan, importance of coastal habitat modeling has been recognized by researchers and government agencies. So continental surveys of coastal habitats are expected even in the future. These are reference what I refer in my talk. I'm sorry, but basically these are report provided by government, but mainly written in Japanese. So that's all. Thank you very much. Thank you for listening.
Thank you, Professor Sangawa, for insightful talk. We have a couple questions for Wensi, please.
Me? Okay. Okay, good. Yeah, thank you very much, Sagawa-san. Yeah, just a very technical question in terms of the, using a remote sensing for coral reef mapping.
Yeah, yes.
Right. You know that very well. It took us a long time, IOC-WESTPAC, to focus on the coastal mapping with a focus on seagrass. There are a lot of discussion about algorithm. So what kind of algorithm you used in Japan to for mapping the coral reef? How is it, how accurate it is?
Yeah, actually, basic technique is the same with the seagrass and seaweed. But big difference thing is actually in Japan, basically highly depends on visual observation and highly depends on field survey. So yeah, basically we conduct a lot of survey and so get a lot of sampling point. And so we adjust to, so first we create temporal map from the satellite image, but we check with the field survey data and we modify if we need. So highly depends on field survey data.
Okay. Okay. Yeah. Right. Right. So that's the issue for some area. If there's no enough human power, right?
Yes,
right.
yeah,
or not accessible.
Yeah,
that's the issue. Right.
That's subject.
Right.
Our next question, Pengbin Wang.
Hello, my name is Pengbin Wang. I have a question. I see when you talk, you referred underwater camera to be used for the seagrass or something. I want to know this technique. All of this is based on for the seagrass or only for part of the survey. It's all of yeah. I see that.
You mean this slide?
Yeah.
Big one.
So I want to know it's how it's the relations with satellites, or it's just a part of developing progress, or all of the surveys based on all of this. Yeah.
Basically here use acoustic camera just for take sampling for remote sensing, and basically under video camera we just check there is seagrass or sandy bottom or seaweed or not. So and using GPS we can know the position in the field. So really simple things we did in Japan.
It's a validation, right?
Yes, use validation and also use for image classification in the remote sensing.
Next,
thank you very much.
Dr. Somkiat, please.
Yeah, thank you very much, Professor Sagawa. I have one question for you. And normally, your cloud truth for the C class, you are using that at co-solder as a the penguin already asked you, but you had some kind of experience, using drone to collect those kind of the data for the something for the cloud truth or for the train, the train this algorithm and in the program to interpret the data.
Yeah. In recently, yes, drone also considered to take sampling. But it's basically it depends on target. You can easily detect, recognize habitat by the drone. I think a drone is also useful tool for collecting data.
Right.
Okay, thank you, Professor Sagawa. And now we open floor for open discussion.
For discussion. Okay. Okay.
Actually, I also have question for both Sagawa and Komatsu, that do we have like things like seasonal dependence in terms of water turbidity, as your study area is in tidal flat, right? So did you experience intervention by seasonal turbidity?
Okay. Concerning about seasonal turbidity, you mean
Like some season water might not too clear to identify.
Okay, I understand. Yeah. Basically, we checked a lot of satellite images. So first selection of the satellite image is really important process in the practical usage. Yeah, actually, sometimes we check the because so far not so many satellite images are used. For example, in some places, we can only have the 10 or 30 satellite images in a year. So basically, we check all the satellite images, and basically we get the better one.
Yeah.
Okay, my experience in the central Honshu Island, the high mountain, like 3,000 meters or like this, and in spring the melted water, melted snow melt, and so water discharged from the river. So in this case, the water is very trouble, not clear. And so in this case, even in spring is a luxuriant growth season of seaweed or seagrass, but we cannot use sometimes. And also in the Tohoku region of east side, in summer, water is not so clear. But in autumn, the Tsushima water current come from the how do you say, north of the Honshu Island, and they come down to south. The water become dramatically clear. So it depends on the season or some reason of clarity. So, but we need to check even in clear water season, the waves are, how do you say, high waves when the swell are like this. Even in the clear water season, but we need to pay attention to the weather conditions. So before the acquisition of satellite data, is it raining or like this and windy, or it is necessary to check the weather conditions before purchase the commercial satellite images. It's it's very important, clear or not, and also the weather conditions before the satellite acquire the image. Okay. So this is my experience.
Thank you. Any other question or point of discussion from the floor?
Yes, Tarachat, if I may. Thank you very much. Yes, I think a very good presentation, 3 presentations we had today. Yeah, from different angles, shed light on how remote sensing inform decision, inform policy, inform, their management. So we actually, I think for people, particularly in South Asia, face the challenge how to develop, the better resolution for coral bleaching, right? I think I heard many people raised the 5-kilometer resolution from NOAA seems it's okay to provide a big background information, but still not good enough, for management, right? At a smaller area, geographic area. So I really think this is a very good demand because everything is demand driven. So based on the demand, how, we can, the remote sensing group people working together with the modelers, with the in situ observation people, to consider kind of some kind of, standard operating procedures rather than doing the research alone. Right? I think from my what I observed, I think our people are working alone in a siloed approach, but there's strong demand there, and also we're lack of that kind of products and service. So I think whether we can come up with some kind of a priority area, that country has a very high attention on that area and very much want to know what kind of situation, right? And also not very easily accessible, pick up some that kind of key area and also combine the different displaying together. And to develop some kind of integrated research plan, of course, including remote sensing monitoring, analysis, come up, like some kind of project, pilot project. Otherwise, I think, yes, we understand remote sensing has limitation. Okay, we understand, some country use this, to do that. But we never know how to really put them together in one side, particularly in developing countries. Right? So there's something, I think, a preliminary thought in my mind after hearing all the 3 wonderful presentations today. Right? If you think feasible, I think we can keep thinking along this line. Either, for, coral reef, seagrass or SEM. But of course, everything need to be demand driven. I think even for Nova case, for Japan case, for the Shizugawa base case, it's a very strong demand driven from behind because the country, because the agency, because of the local government really want to know what's happening and what changed. So this is not just from research basis. This is really from social, economic, environmental challenges as a driving force, to make that kind of a result happen. So this is just my preliminary thought I would like to share. Yeah.
I really agree with when Mr. Ng. Yeah, I will do a collaboration research with institute researcher too. I also thinking in Japan.
Right.
And maybe we also introduce institute researcher to this conference as well. Maybe.
Right. I think that's something we can say the impact of our research, right? Not only paper, but also really the benefits generated from research for different stakeholders. I think this is something we should intensify our efforts for the future remote sensing work. And also enjoy working with a different discipline, different people, right? Coral reef expert, ecologists, to learn from them as well, right?
Yeah, Wenji, thank you very much for your comment. I think it is a very good occasion to use satellite, Japanese satellite, L3. It's a 4-meter resolution, very good. And if we set, WESTPAC can set some super site where the ecologists and mapping people or social science conduct the research to resolve some problems. If we can do it, it's a very nice. But in this case, WESTPAC takes the initiative to set some, one area is okay. Even, for example, in Thailand, for example. And we collaborate, or the WESTPAC researchers to make some, research. So I think it is a very good occasion to use the Japanese satellite. It's L3. It's
free, right?
Not free, but I am a PI of this project, so I can provide.
Okay, good. Right.
Yeah, it's a very nice, good super site,
Okay, nice.
Okay, thank you. I have to leave to another meeting. I'm sorry, but thank you very much today.
Thank you very much, Sakawa-san, for your time and also wonderful presentation today. Yeah, as I said, keep engaging with us, right?
Yeah.
We look forward to see you next year in person.
Okay,
right.
You.
Right.
Bye.
Take care. All the best.
Okay.
Right.
All right. I think we shall close for today. But before leaving, we want to capture a group photo.
Group photo? Okay.
It might be too late, but
it's okay. Never too late. Never too late.
We're still in group.
All right.
Okay.
Everyone, if you are convenient, please turn on camera, please.
Oh, not bad. We have almost 50, actually, right? More than 50 people today. Thank you. I think I really enjoyed the 3 talks today.
Thank you everyone for joining us today and staying up to this moment. And I will wait.
Oh, Ken. Oh, you should share your idea, Ken. Yeah, please turn on your camera.
All right, guys, I will caption. Oh, some more.
Okay, Tamasaka also there. Good.
All right, 1, 2, 3. 1, 2, 3. All right, 1, 2, 3. Thank you, everyone. And okay, we close for today. And next week we can have 3 speakers again every Tuesday morning.
Yeah, next
You
Tuesday,
can,
same time, right?
yeah, you can use the same Zoom link to enter.
Thank you very much, Touchnet, for your moderation today. We really expect through this webinar series, we can get more good ideas, from the remote sensing community and the other associated or relevant stakeholder groups, through discussion. Because next year we will have intergovernmental session of IOC-WESTPAC, and also we will have the UN Decade Ocean Science Conference next year in conjunction with the traditional WESTPAC International Marine Science Conference. So we try to initiate something new or activities, building on efforts we have been doing in the past. So keep engaged, right? And also look forward to more excitement in the near future that will be generated from this group. See you next Tuesday.
See you.
Thank you very much.
Right.
See you soon.
Thank you.
Bye-bye.
Bye.
See you next Tuesday.